Okay, thank you for giving me an opportunity to give that talk, and I'm sorry I cannot give it in person. Hope next year it would be better and I'll be able to come. I'm going to tell you something about the loop corrections to the dynamical Casimir effect and the summation of these loop corrections. Well, it may be not exactly about curved spacetimes, but dynamical Casimir effect is often thought of as a toy model of particle creation in curved spacetimes such as expanding universe, like Friedmann metric, or black holes. For example, you can see that the equations of motions are very similar and the action is very similar. And the effects of particle creations in this model is very similar to the particle creation in curved spacetimes. However, dynamical Casimir effect has a very great advantage. It can be measured experimentally in some models, in some squid arrays, so-called, or superconducting quantum circuits. So these predictions which we make for the dynamical Casimir effect can be checked experimentally, and that is very great, I think, when we have something to adjust our models with the reality. So first, a few words about a traditional look at the particle creation in non-stationary systems. Usually, if we have some non-stationary system, for simplicity, let it be stationary, that's asymptotic past and future, but we have some motion between these asymptotic regions. Usually, one expands the quantized field over in modes and out modes with some creation and negation operators, which are not identical because our system is dynamical and vacuum and the asymptotic past and future do not coincide. But these creation and negation operators and in and out modes are related with the Bogoliubov transformation, which is as follows, with some Bogoliubov coefficients, which are determined by the motion of the system, how space expands or how mirrors move. The dynamical Casimir effect is about moving mirrors. Then, when we have this Bogoliubov transformation, we can relate the creation and negation operators in the asymptotic past and future, and calculate the particle number, or let's say energy, or just level density, which is as follows, and anomalous quantum average or correlated power density, which is as follows. And if we are starting from vacuum state, you have formulas like boxed formulas. And if you have some initial population of levels or initial related particle densities, you have also corrections to these formulas. For example, in thermal state, you should substitute the corresponding quantities here, here, and here. But if we start from vacuum, we have just these simple expressions. And usually, when one discusses particle creation, one thinks about this formula. Nevertheless, and this is not always right to think in these terms, because these formulas are written for the free theories, where we can have more decompositions. And usually theories contain interactions, like particle scattering, or one particle decaying into three, and so on. And if we have this interaction, then the quantum averages like n and kappa will receive loop corrections. This may seem an innocuous problem, but actually these loop corrections will grow secularly, like in the top of the previous, like in the top of Prokopy, which means that the powers of a small quantum constant will be accompanied by the powers of large evolution times, which will say that the initial state of our system will change. If we start from the vacuum state, we will not only have this vacuum state appear to be non-populated in the asymptotic, from the point of view of asymptotic future observer, but the state itself will also change. And this is a problem. And if we want to estimate observable quantities like correlation functions or stress energy tensor, we have to sum up these secular loop corrections. And today I try to give you a glimpse of how it is done in the dynamical Casimir effect with moving mirrors. Okay, first let me say also a few words about the tree-level case, what have been done long ago, approximately 20 years ago. We will consider for simplicity the scalar Casimir effect, not a real electromagnetic field by just only one of its components. And we will assume that this field is massless. That is, we will consider the following equations of motions. It's just massless Klein-Gordon field, but with the directly boundary conditions which are changing with time. And for simplicity, we will fix the left mirror, the LFT, and let the other mirror, the right mirror, move in the region between times 0 and t large. We will also assume that this moving is not too big, that the relative change of the coordinate of the right mirror is not very large. We will assume that this epsilon is small, but it still may be substantial due to the resonance. Well, the inMOS in this case can be written as follows, where the function g solves the Morse equation. And if we assume that this motion is non-resonant and the relative change of the coordinate of the right mirror is not large, then one can easily show that the function g remains close to linear in the asymptotic future region. It can be approximated by the following formula, where the coefficients g can be calculated explicitly if we know the trajectories of the right mirror, the trajectory of the right mirror. But what's important is that these coefficients are still small, that is, they are proportional to this small number epsilon. Then we can calculate Bogoliubov coefficients, which will be almost identical. And we can calculate the corrections to the quantum averages, which are also very small in this case. And that's not surprising, because if we move mirror slowly and non-resonantly, we pump a little energy into it, and no levels are excited, no quantum averages are generated. However, if we consider a resonant motion, for example, a following motion at twice the fundamental frequency, and oscillations at twice the fundamental frequency of our cavity, then the solution of the Morse equation is very different. It looks like a staircase that at large evolution times, and it was calculated nearly 30 years ago. And in this case, Bogoliubov coefficients are as follows: they are not close to the identical. Then the Bogoliubov transformation is not close to identical. And if we calculate the n and kappa in that case, we will see that they grow linearly with time. That is, they are that means that we pump a lot of energy in the system, and it excites us significantly. Well, now let us consider loop corrections to these results. That is, let us turn on interactions. For simplicity, we consider quartic interaction, but it's not. But we can consider others as well. In the non-resonant case, since the number of created particles and the population of the levels are not very large, in fact, the corrections can be calculated directly from the decomposition of the evolution operator, at least in the following limit, when we single out the leading loop corrections. In that case, the evolution operator can be roughly approximated as the following exponent with just time-dependent Hamiltonian, effective Hamiltonian, which we can get by substituting the inMOS into the original interacting Hamiltonian and neglecting rapid latent terms. In fact, this Hamiltonian looks as follows if we additionally decompose it into the powers of epsilon, which is a small number. The leading contribution is just the Hamiltonian of the stationary problem. It says that the energy in the collisions of particles is conserved. Either one particle turns into three, or two particles scatter off each other. However, the subleading correction contains the processes that include as well the latent energy processes. For example, this term describes the creation of four quanta from the creation of four quanta. And then if we substitute this effective Hamiltonian into the formula and estimate the leading corrections to the quantum averages, we will see that they now oscillate near non-zero values. However, they still remain small. They are still proportional to this small number epsilon squared, but they are comparable to the true level values, which is remarkable already. Now let us discuss the more important case, the resonant case, which is usually implemented in practice, and in which case already at the true level the quantum averages grow significantly. In this case, it is convenient to use the Schwinger-Keldysh technique because the Keldysh propagator contains the interesting to us quantum corrections to the quantum averages and kappa. And we will again single out only the leading secular Gaussian corrections. That is, we will consider the following limit for the correlation function for this Keldysh propagator. And if we look at the Schwinger-Keldysh technique and the behavior of propagators in the resonant case, we will see that in fact most of the corrections are suppressed and only few survive, and a few diagrams survive. To see this, we need to make four crucial observations. First, we always can map the trajectories of mirrors into the stationary ones, that is to standing mirrors. Since we consider interactions, we will get this transformation at the cost of the conformal factor in the direction vertices. We have integrations in the direction vertices, and now this integration should be done with the conformal factor of this transformation that maps the moving mirrors trajectories to the stationary ones. Second, we expect that the leading secular contributions come from large evolution times, as it usually happens when we consider loop corrections in non-stationary separation. Third, we can see that if we calculate Bogoliubov coefficients in the resonant case, flash variation times, they start quickly decay if we consider momenta larger than the following momentum. That is, we can impose ultraviolet cutoff in these integrals in vertices. And finally, we can see that if we do all this, then only the diagrams with the internal retarded or with only internal Keldysh propagators will survive, because if the diagram will contain some internal retarded advanced propagator, then its contribution will be suppressed by the powers of the coupling constant, which is small, and will give the subleading secular contributions, and we were looking only at the leading contributions, and hence we can neglect these diagrams. If we do all this, we can estimate the corrections to the quantum averages and then kappa, and we see that this time they not only small, they are much larger than the true level contributions, parametrically larger. They contain these large factors. And this result is easily generalized to non-quartic interactions, for example, some interactions which is realized in the experiments with superconducting quantum circuits. And this is, of course, only an approximate result in the following limits. But if we will somehow get to these times at the experiments, then we can expect that loop corrections will be visible. They are not visible in the current experiments because the quality of circuits where they model this dynamic Casimir effect is not so large, and so in practice the experimentators deal with times less than this characteristic time. But if they will somehow increase the quality of the cavities they model, I expect them to get to this regime. So, so I have told you about a few key results about. I tried not to give much into details. Hope I managed to do this. I told you how to calculate relation, the loop corrections to the correlation functions and quantum averages in the dynamical Casimir effect, which is the creation of particles by moving mirrors. And we see that if we consider non-resonant case, then the loop corrections are comparable to the true-level quantities, but they still remain small as true-level quantities. And we consider the resonant case, loop corrections are not only large, but they even exceed the true-level contributions. So this may motivate the experimentators, or this may motivate us to search for something similar in the theories of quantum field and curved spacetimes, something like that. Thank you for listening. I'm ready to answer questions if you have any.
Thank you very much. I think we have time for one question, maybe. Okay, one question.
Hi, and thank you for the nice talk. Now, I wonder if anyone has ever tried to study the same behavior with loop corrections by considering, by localizing, let's say, the modes with wave packets, for example.
Yes, it would be interesting, but I haven't done that.
Okay, thank you.
Well, in fact, the choice of the initial vacuum state is a good choice. In practice, usually we have a thermal state with some. It would be more interesting to generalize these results to some initial occupations, like in thermal states, because if we have experimental setup, it's usually in not vacuum state. It's usually has some temperature. So that would be more promising, but wave packets also deserve some tension, I think.
Yeah, I was thinking because in that case, maybe you can just study, for example, the particle production just in the acceleration time of the mirror.
Yeah. That's a great idea.
Okay, thanks for your question. Maybe if it's very fast, we have time for a second question.
Hi, just wanted to ask, so you say loop corrections significantly exceed the 3-level values, which seems to imply that actually the perturbation theory breaks down. Maybe
well, yes, but that's
a regime where
well,
stopping there is not enough.
yes, let me emphasize that I work just in this limit. I calculate loop corrections only in this limit, and I don't know what happens for larger times. And I say that loop corrections are significant only at these times. So I say that my results are applicable only there, and obviously they're not applying. They can be extended to larger times. There we need to take into account the high order loop corrections. We cannot just restrict ourselves only to the leading contributions. Of course, the perturbation theory is breaking down, and here I just tried to estimate the leading contribution.
Okay, thank you. Thank you very much.